guys, and welcome back to the YOLO series. And in this video, we're going to take a look at the next version in the series known as YOLOX. And YOLOX is considered as an outlier when compared to the previous versions of the YOLO model due to the fact that it uses unconventional techniques that wasn't implemented in the previous versions. And as we go further along the video, we're going to see why that's the case. First, let me give you an introduction about the YOLOX model. YOLOX is YOLO's new high-performance object detection algorithm. Unlike previous YOLO algorithms, it includes three fundamental innovations. These are decoupled head, anchor-free, and advanced label assigning strategy. With these innovations, YOLOX provides better performance in speed and performance than its counterparts. So YOLOX introduces a different technique that wasn't originally implemented in the YOLO series, and it uses a strategy called decoupled head, where they split the head output from the previous YOLO models and decoupled it and split it into different tensors. And the previous YOLO models always used the anchor boxes in order to make predictions about the bounding boxes. But in YOLOX, they have completely removed the requirement for anchor boxes, and we will see why they try to implement an anchor-free model. And they also used an advanced label assigning strategies, which is different from the previous YOLO models. So anchor-free detectors, advanced label assignment strategies, and end-to-end detectors are the most important focus points in object detection lately. And these new focal points are still not integrated into the YOLO, and YOLO v4 and YOLO v5 are still anchor-based detectors and uses handcrafted assigning rules for training. It is an important reason for the development of the YOLOX algorithm. So now let's start by looking at the backbone for the YOLOX model. As we have seen previously in the YOLO v3 video, the YOLO v3 algorithm is the basis for many object detection algorithms and is also what YOLOX uses. So you can also go back to that video and try to revise some of the points that we have discussed about YOLO v3 in order to refresh your mind about some of these concepts. But in that video, we have mentioned that YOLO v3 uses a large backbone called the darknet 53. And this is a backbone that is also used in YOLOX model. And it has the architecture that we see on the left side. And there are a bunch of convolutional blocks and residual blocks. And the ones that are shown inside of the rectangle are called residual blocks, as they have residual connections. And they always implement a 1x1 and 3x3 convolutions. So the darknet backbone and its three outputs. So when we discussed about the YOLO v3 model, we have seen that it has outputs at three different scales. And the first one, as we can see from the image on the left side, starts from the third residual block. And we add a bunch of convolutions and also rescaling. And we also have a second output at a different scale and a third output. And all of these outputs are coupled, which means they are combined, and we use a large tensor in order to represent all of the predictions at the three different scales. So essentially the darknet 53 backbone, which I may call ZFPN from now on, because in the transition between the YOLO head And the backbone, we have the feature pyramid network in YOLO v3, and outputs 3 different predictions at different scales. And for the first transition output, we have 256 channels. And for the second one, we have 512. And for the third one, we have 1024 channels. So the darknet backbone and 3 outputs. Each of these outputs extracts information at a different scale. Notice how the number of channels increases as the length and width of the image decreases. So as we can see on the 3 different scales, as we go down, the height and width of the image decreases. First, we're dividing the height and width by 8 from the original image to get the first output. And for the second output, we're dividing the original height and width to get a feature map of height divided by 16 and width divided by 16. And we also divided third outputs height and width by 32. So the 256 channels transition output extracts features at a smaller scale, while the 1024 channel outputs extracts features at a larger scale, since the 1024 channel output has less information from the original image to work with. So as we have seen previously in the YOLO v3 video, we have mentioned that the first output is going to make predictions for at a smaller scale, and the third output is going to make predictions for larger objects, because since the first output is deeper, or it's not deeper, but it's actually in the shallower part of the network, it has more representation and information to make predictions about small objects. But the last one, since it's deeper inside the network, it has to make predictions for larger objects. But since it doesn't contain that much information as the first output, we increase the number of channels as we go down. Since we are shrinking down the spatial information, we are increasing the channel information. So one major difference between YOLOX and the previous model YOLO v3 is the head part of the network. And we have seen that there are similarities between the YOLO v3 and YOLO v4 model because they have the same head. But for the YOLOX model, we are going to use a different method to represent the output from the model. And the YOLOX model uses the YOLO v3 model as a baseline, and they do not use the YOLO v4 model as a baseline. And that's one point that we have to pay attention to, because the YOLO v4 model as a backbone uses the CSP darknet 53 model, but YOLO v3 uses the darknet 53. So they used the backbone of YOLO v3 as a reference point and start expanding from there in order to make the YOLOX model. Although the YOLO v3 backbone and the YOLOX backbone are the same, the models begin to differ from their heads. So this is an image that represents the difference between the YOLO v3 to YOLO v5 coupled head method. And as we can see, if this is the output from one of those outputs that we have seen in the previous slide, we can divide them into height times width, which is going to represent the spatial information. And in channel wise, we have the number of anchors multiplied by the class. These are the class score. For example, if our model has 80 different classes, so C will be equal to 80. And the second one will represent the number of anchors multiplied by 4, where 4 represents the 4 coordinate points, X, Y, W, and H, for the bounding box regressor. And finally, we have the number of anchors multiplied by 1, which is the objectness score, and that will give us the dimension across the channel. But in terms of YOLOX, as we can see, the final output is going to be decoupled into two components first, and we're going to pass it through some convolutions first, and then we're going to split all of these components which are coupled from YOLO v3 to YOLO v5, and we're going to split the class and the regressor and the IOU, which is a decoupled representation of the final output from the YOLO model. So when I first saw this diagram, I found it a little bit confusing. So below is a marked up version of the diagram, which I hope makes it a little bit easier to understand. So as we can see, for the first coupled head from YOLO v3 up to YOLO v5, we use a one by one convolution, additional convolution from the final feature map representation. Then after we pass it through a one by one convolution, we have the final representation, which is going to represent the class, the regressor, and the objectness score. But in terms of YOLOX, first, we also do the same convolution operation that we have performed before. We're going to convolve it with a one by one kernel. Then we're going to split it into two, and we're going to pass the height, width, and the class of each BCE loss is going to be, so we're splitting the channel-wise component, and the component that only contains the class information is going to pass through two 3x3 convolutions. And then here we can see that there is a times 2, which is upscaling or the spatial dimension. Then finally, we're going to perform a one by one convolution. And then we have the feature map representation only for the class score. And then for the second component, we're going to pass both the regressor and objectness score, a part of the feature map, and then we're going to convolve it with two 3x3 kernels, and then finally we're going to split it into two other components, and we're going to pass both through one by one kernels or convolutions, and then finally we have the feature map for the regressor and the objectness score of each of the bounding box predictions. So when we compare the two heads, this diagram is stating that the input into both the YOLO v3 head and the YOLOX head is the three outputs from the FPN backbone at three different scales. So one thing to notice is that this is just only a representation of one of the outputs from the YOLO v3 model. And as we have seen from the previous slide, we have seen outputs from three different scales, which have feature map representations of 256, 512, and 1024 channels. And each of them have a feature map representation, which is shown here. And we're going to actually multiply this by 3, since we have outputs from three different scales. And we're going to split them into 3. So we're going to split each output into class score, regression, and objectness score. So the output of the two heads is essentially the exact same with dimensions height multiplied by W multiplied by features, which is just like the original YOLO. So it's talking about this representation. And the difference between the two heads is that YOLO v3 uses a coupled head and YOLOX uses a decoupled head. So we're splitting this into 3 different components. So the output of YOLOX is actually 3 tensors, each holding different information instead of one massive tensor with all of the information. So the YOLOX output is containing 3 different tensors representing the different parameters explaining each bounding box. But in terms of YOLO v3 up to YOLO v5, we're just using one massive tensor in order to represent all of the information about the bounding box prediction. So as we can see from the right, we have the three different outputs from the YOLO v3 model. And while decoupling, we're going to split each of these outputs into three different components. So we have three outputs here, and three outputs here. And in total, we're going to have 9 different outputs. And the three tensors YOLOX outputs hold the same information as the massive tensor YOLO v3 outputs. So the outputs are the same, but they just split the massive tensor into three smaller components. The first one contains the class of each bounding box. The second one contains the regression points, the 4 parts of the bounding box, which explains the position x, y, and the width and height of the bounding box. And finally, we have the objectness score. For some reason, the authors use IOU instead of OBJ to represent the objectness score. But this output is just how confident is the network that there is an object in the bounding box. So it's basically the same definition as before, but they change the label IOU instead of OBJ. So just like with original output, each pixel in the height and width of the output is a different bounding box prediction. So there are height times width different predictions. So each of the outputs have height and width, and we're going to make bounding box predictions on each of the pixels across the height and width, and the channel dimension represents the class score, the regression, and the objectness score. And the outputs listed above are only for a single output in the FPN. Remember, there are 3 outputs from the FPN, which are fed into the heads of YOLO v3 and YOLOX. So just remember that we are using, this is a representation for a single output. And each of these 3 are going to be decoupled before being fed into the head part of the model. This means there are actually 3 different outputs from each of the heads instead of 1. So we have 3 different outputs from each of the head instead of just 1. So the output of YOLO v3 is actually 3 multiplied by height multiplied by width multiplied by number of features. And the output of YOLOX is actually 3 of each of the class regression and IOU outputs, making 9 total outputs. So we have 3 multiplied by height multiplied by W multiplied by features is the output from the actual YOLO v3. And each of these are going to have 3 different outputs. So we're going to have 9 total outputs in case of YOLOX. Now we have finished the first part of the YOLOX model, which is understanding the decoupled head that they have introduced in the paper. And the second one is using an anchor-free model. So one of the most important changes YOLOX has made was not using anchors, whereas YOLO v3 heavily relies on anchor boxes. So basically, if you have seen our the video that I've made about anchor boxes, it is just a way to help the model so it doesn't have to directly predict a bounding box. So originally, the YOLO authors needed anchor boxes in order to make predictions or in order to make predictions about the offsets for the predicted bounding boxes. So they use the anchor boxes as reference points, and they just expand them or resize them in order to make them fit the predicted bounding boxes. Although anchor boxes allow us to find more than one object in the same grid, they have some disadvantages. And on this slide, we're going to discuss about the problem with anchor boxes. First of all, optimal anchor boxes should be determined for an optimal object detection. For this reason, we try to find optimal anchor boxes with clustering analysis before training. This is an extra workload and a waste of time for us, because since we are going to adjust the anchor boxes in order to predict the bounding boxes, first we have to select optimal anchor boxes before the training begins, because these anchor boxes must be optimized in order to make better predictions for the bounding boxes. We're not going to select random anchor boxes out of the box, but we're going to use a clustering method or a clustering analysis method in order to select the best anchor boxes that are going to make predictions for the bounding boxes. But this procedure is an extra workload and a waste of time for us. And another problem is that the anchor box structure mechanism increases the number of predictions to be made for each image. This can cause delays and slowdowns on some systems. Since we are using anchor boxes to make predictions for the bounding boxes, there are going to be a lot of predictions, and each of these predictions are going to cause a delay or a slowdown in our system. But in recent years, it has been determined that anchor-free systems are successful as anchor-based systems. So the authors in the YOLOX paper just basically said we don't need anchor boxes anymore. What if we just completely remove them and come up with a new method in order to make predictions about the bounding boxes, because the anchor boxes are burdening our system or causing delays on the system. So in order to remove that strain coming from the anchor boxes, they developed an anchor-free system. With anchor-free systems, similar success has been achieved, and the design parameters have decreased and the speed has increased. So how does the YOLOX model fix the anchor box problem? YOLOX simply has the model directly predict the bounding box dimensions as opposed to predicting an offset from an anchor box. So it's just predicting the bounding box directly without relying on the anchor boxes to make those predictions. So to directly predict a bounding box, YOLOX uses a decoupled head that we have seen in the previous slide, and additionally it uses something called striding. So if you completely remove the requirement of anchor boxes to make predictions, they have to come up with a different method to make those predictions, but without all of the drawbacks that are introduced with the anchor boxes. So that method that they come up with is called striding. YOLOX was not just based on YOLO v3, it was also based on FCOS, which is another bounding box model, but it's not part of the YOLO series, making it not very cool. So striding, FCOS uses striding to help the model out. Imagine the model has to learn to predict a bounding box anywhere from the top left of an image at 0, 0 to the bottom right of an image at 1024 to 1024. So there is a method known as FCOS, and it uses striding to help the YOLOX model. And if we consider the YOLOX model making predictions starting from the top left corner of the image to the bottom right corner. Let's say the dimension of the image is 1024 by 1024. In a discrete space, the model has to make 1,048,576 possible locations to predict from, and it will likely not be able to learn anything new due to this wide range of predictions. So if they just basically start from the top left corner to the bottom right, there are going to be an enormous number of possible locations where the prediction can be made, that it's not feasible to implement this kind of method. So striding fixes this issue and allows the model to predict from an offset as opposed to from the top left part of the image. So they use a technique called striding, and this method allows the model to predict from an offset of an intersection point rather than the top left corner of the image. So what is this striding technique in general? So basically we can split the image up into a grid based on 3 different scales the model will make predictions at. So if we have an image with a cat, then we can basically divide the image into multiple grids, and using these grids we can assign each prediction to each of the intersection points on the grid. So once we construct the grid, we're going to make predictions on each of the intersection points on the grid. The nice part about the predictions from the YOLOX model is they are already in a length times width format. So we can directly map each of the outputs to a unique point on the grid and then use that grid point as an offset to scale the bounding box. So previously we said that we can consider all of the points across the height and width in order to make the predictions. But the drawback from this kind of method is that we have to make predictions with respect to the top left corner of the image. And across the space, we have seen that there are around 1 million possible locations in the space of 1024 by 1024, and that's not feasible. So that's why we're using the intersection points of a grid system as an offset in order to make the predictions instead of the top left corner of the image. So we can directly map each of the outputs to a unique point on the grid and then use that grid point as an offset to scale the bounding box. So what we're doing is we're mapping the outputs to a unique point on the grid. So for example, if we want to make predictions here, we're going to use the intersection point as an offset in order to resize and scale the bounding box to make the predictions. Notice that we are not using anchor points, anchor boxes, not anchor points, in order to make those predictions in previous YOLO models. But now we're just using a grid system and an intersection point to make those predictions. The grids above can be created by defining a certain stride, which is the distance between each of the intersection points on the grid. So striding, or a stride, is just a concept which explains the distance between each of the intersection points. So in the YOLOX algorithm, strides of 32, 16, and 8 are used for each FPN level respectively. And if a stride of 32 is used on a 256 by 256 image, then there will be 256 divided by 32, 8 intersection points on each dimension, totaling 64 intersection points. So here on the image, we can see that these are predictions across the 3 different scales, and the strides that we use for each of the scales are mentioned here. So for example, for the first scale, we can use a stride of 32, and if the image is, if the output height and width is given as 256 by 256, then we divide that the height or width by 32, which is the stride, and we get the intersection points. Then finally, on each dimension, we have 64 intersection points. So these are the intersection points that it's talking about. So, in general, the following image has the grid overlay for the bare image at 3 different levels with different stride. So this is the image for level 1 with a stride of 32, and this is an image for level 2 and for level 3. Each intersection point on the image is called an anchor point. So each of these intersection points that we see on the grid are also known as an anchor point. Notice that an anchor point is an offset to move the XY location of a prediction, while the anchor box explained previously, which is what YOLOX gets rid of, is a predefined box that is used as an offset for the WH parts of a prediction. So we have to understand the difference between anchor point and anchor box. An anchor point are each of these intersection points that are implemented in the YOLOX model, but an anchor box is a predefined box which is used as an offset to make the predictions for the bounding boxes. So the anchor location on the image can be obtained with the following formula. So we have the x and y. So these are the coordinates for the predicted bounding box, which are implemented the same way as before. But in order to calculate them using the new method, we have to use the stride, which is represented by the variable s, and I is the i's intersection point on the x-axis, and j is the j's intersection point on the y-axis. So by using the coordinates of the intersection point on the image, then we multiply by the stride used on that scale, and we add it to the stride divided by 2 in order to find the x and y coordinates for the predicted bounding box. For example, let's go back to the bare image with a stride of 32. If the anchor point for this prediction was ij, and this is this point as we can see on the figure from the right, and let's say the I variable is assigned to 2 across the x-axis because we moved 2 boxes to the right, and since we just moved 1 box from above, let's assign a value of 1 to j, meaning the intersection point 2 on the x-axis and 1 on the y-axis. I would be looking at the following point on the image. The point is at 2, 1 on the grid, but pixel-wise, it is at 80 and 48, and this is computed by using the formula that we have seen on the previous slide. We replace the 2 and 1 on the x in order to compute the x and y, and as you can see here, we have used a stride of 32, and finally we have a pixel-wise output of 80 and 48. in order to get this red point. For YOLO X, we use the grid points on the top left offsets of the bounding box. And the following formulas are used to map a predicted bounding box, px, py, pw, and ph, to the actual location on the image, lx, ly, lw, and lh, if xy is the intersection point on the grid, which is the prediction belongs to, and S is the stride at the current FPM level. So the grid points that we have computed before are going to act as the top left offsets of the bounding box. So we have mentioned that we're not using the anchor boxes in order to make the predictions for the X, Y, W, and H of the bounding boxes. But instead, we're going to use the intersection points of the grids that we have implemented to act as the top left offsets for the bounding box. So the coordinates Lx, Ly, Lw, and H just represent the xy coordinates for the bounding box and the width and height for the predicted bounding box. And they're going to be computed from xy, which is the coordinate for the intersection point or the anchor point. And we're going to add px, py, pw, and ph in order to compute lh, ly, lw, and lh. And this formula is actually familiar because we have seen in the previous video about YOLO v3 how to get these points. And it's kind of similar, but we're using strides and intersection points in order to make these predictions instead of using the predefined anchor boxes. So we move the predicted point by adding the prediction to the anchor, the xy point assigned to this prediction. So if we have a bounding box and this bounding box is assigned to one of the intersection points xy, then we're going to add the prediction from our model. So px, py, pw, and ph are all predictions from our model. And then we're going to move that bounding box with respect to these predictions in order to find the new location until it overlaps with the ground truth bounding box. So we also denormalize the width and height by ensuring it's not negative with an exponential function and moving it based on the stride of an image. So here we're using an exponential function so that it falls between, so it's a normalized value, and then we're going to multiply it by the stride based on the scale. So let's consider an example. If the model gave me the prediction 20, 15, 0.2, and 0.3 for the width and height, then we can calculate the box as this, and we get a value of 100 for the x value, and we get a value of 63 for the y value, and we get 39 for LW and 43 for LH. And these values are predictions from our model, and we'll place them instead of the px and py. And the original x and y are given as 80 and 48, which we computed from the previous slide. And these 0.2 and 0.3 are predictions for the scale of the width and height. And we pass them inside of an exponential function, and then we multiply by a stride value of 32 in order to get the final predictions for the width and height. And just by using that intersection point, we have found a bounding box. So the final image may look like the following. But notice that this bounding box is not overlapping with the object. So that's the job of training the model, because we're going to modify the outputs from the model, and we're going to modify these values until we find the best bounding box. So we have covered all of the points about anchor-free systems. Now we're going to talk about label assignment. Not all predictions are equal. Some are clearly garbage and we don't even want our model to optimize them. So to differentiate between good and bad predictions, YOLOX uses something called SMOTA, which is used for dynamic label assignment. So if we have an image and we want to detect an object inside of the image, most of the predictions are going to be garbage or negative predictions or background, because we're going to select an object in some of the positions, but that's not always the case when we go through all of the pixels inside the image. So these bad predictions will overwhelm our system, and these good predictions are very small when compared to the bad predictions. So one thing you might have learned about classification models, if there is a class imbalance, which means you have more number of cases for one class, but less number of cases for the other class, then your model is going to struggle to make predictions. So that's the case. That's also the case in object detection, because there is going to be a class imbalance between the bad predictions and the good predictions. And predictions that are thought of as good, which bound a ground truth object, are labeled as positive, and those that are bad, which bound the background, are labeled as negative. And SimOTA doesn't just assign positive or negative labels, but it also assigns the ground truth bounding boxes to each positively labeled anchor in the image. If it selects a single positive sample, it ignores other predictions even if they are of high quality. So one way to address this problem, or the class imbalance problem, is to use an approach known as dynamic label assignment. And what they did was not just assigning positive and negative labels, but in order to associate those positively labeled anchors with the ground truth bounding boxes. So all of the predictions that are associated with the ground truth bounding boxes are positively labeled anchors in the image, so that if it selects a single positive sample, it ignores other predictions. So since the bad predictions will overwhelm the system, we're going to select only the positively labeled anchors and ignore all the other predictions which are associated with the background and not the ground truth bounding boxes, even if they are of high quality. Next, we're going to see the loss function that was used in the YOLOX model. There are three outputs to the YOLOX model, and each output has its own loss function, and they need to be optimized in different ways. So we have seen that we have a decoupled head in the case of YOLOX, and we have a feature map that represents the class course, and we have another feature map that represents the regressor, and finally we have one final feature map that represents the object and score. And we need to calculate the loss for each of these parts of the feature map. And the three different losses include the class loss, regression loss, and object loss. And the final loss function is just a combination of the three losses stated above and is defined as follows. So the loss function is basically the sum of all of the losses averaged over the number of positive labels. So in the previous slide, we have mentioned the case of class imbalance problem. And in order to address that problem, they have selected only the number of positive cases and ignore the negative predictions so that they don't overwhelm our system. And since we have a count of the number of positive labels, then we're going to average each of the losses by the number of positive labels. And remember, we used a SimOTA to assign the labels to each prediction. So this technique was used in order to assign the positive label to each of the boxes. And the variable reg weight, which is a weight used for the regressor, is just a balancing term used to weigh the regression loss over the other losses, and it's most important to optimize. And the authors use a weight of 5.0. Since the regressor loss is more important than the class loss and the objectness score loss, they associated a much higher weight to the regressor so that the model will learn to optimize the regressor more than the class and the objectness score, and they just used a value of 5 in case of YOLOX. Finally, they used, during the training, they used different data augmentations, data augmentation techniques, along with YOLOX random horizontal flip, color jitter, and multi-scale were used in the data augmentation part. So random resized crop, which was used for data augmentation in the previous YOLO versions, is no longer used. So they used some data augmentation techniques that weren't implemented in the previous YOLO versions, and they removed the random resized crop data augmentation technique from the previous YOLO versions. And YOLOX does not use the random resized crop, as the random resized crop strategy is countered by the mosaic augmentation. Mosaic augmentation is one of the bag of freebies which was implemented in YOLO v4, where we stitch 4 different images together in order to optimize the model during training. But since the random resized crop strategy was already countered by the mosaic augmentation, they dropped this technique in YOLOX model. Another data augmentation method added to the YOLOX is the mix-up. Although mix-up was originally a data augmentation method developed for image classification, it has become usable for object detection with bag of freebies. As an important point, after the mix-up and mosaic data augmentation methods, ImageNet pre-training, which was used before, has been abandoned, and train all the following models from scratch. So after the mix-up and mosaic data augmentations, which was used in the ImageNet pre-training, they have been abandoned, and they have trained all of the following models from scratch. So next, we're going to discuss about the end-to-end learning that they have implemented, but was considered as optional because it didn't provide that much improvement. And one of the most important points in machine learning is to decide which problem to solve with which algorithm. And there may be more than one algorithm to solve a problem, and we need to decide which one to use. End-to-end learning is a solution to a comprehensive goal using a single and complex deep learning model. So end-to-end learning is just a technique or a solution provided so that it can help us to decide which problem to solve by using which algorithm. So there may be more than one algorithm that may be available to address that problem. And in order to decide which one to use, we can use a technique known as end-to-end learning. And YOLOX added two more convolutional layers to the YOLO model. The first one is a one-to-one label assignment, and the second one is a stop gradient. And these ensure that the detector is end-to-end. However, since they cause a slight decrease in the performance and inference speed, they're not added to the final version of YOLOX and are offered as optional. So as we can see from the table on the right side, we can see that the vanilla YOLO, which is a YOLO that do not use an end-to-end method. For the coupled head, we have an average precision in the COCO dataset of 38.5. And in the case of the decoupled head, we have 39.6. And then when they implemented the end-to-end strategy for the YOLO model, there's actually a decrease in performance, or in terms of average precision for the coupled and decoupled head. Here we can see there is a minus 4.2 drop from 38.5. And in the case of a decoupled head, we have a drop of 0.8 from the original vanilla YOLO. So since there is a slight decrease in the performance and inference speed, they're not added to the final version of YOLOX, and they are offered as optional. YOLOX model also considers different backbones other than the Darknet 53 backbone, so that it can be used on different computational devices. So you can check the different YOLOX versions and their performance in this table. So there is a small version, a medium, large, and extra large version for the YOLOX, and the corresponding performance improvement from the YOLO v5 model is shown on the table. So for the YOLOX small model, we have a gain of 2.9%, and we actually increase the number of parameters. And these are the G-flops and the latency of each of the models. And in each case, we can see that we have much more improvement from the YOLO v5 model. And here we can see that the YOLO v3 ultralytics model, and this is just a PyTorch implementation of the YOLO v3 model. And by using the YOLO v3 as a baseline and introducing all of the techniques that we have mentioned previously, such as introducing the decoupled head from the YOLO v3 baseline model, gave an improvement of 1.1. And by using strong augmentation techniques that we have mentioned before, they have produced a gain of 2.4. And when they removed the anchor boxes and implemented the anchor-free strategy, they got a gain of 0.9. And by using the case of multi-positives, or the positive labels that we have mentioned before, they also got a gain of 2.1. And finally, by using the SIM OTA strategy, they also got a gain of 2.3. And finally, by using non-maximum suppression free as optional, it actually decreased the performance, so they just dropped this strategy. So finally, when we take a look at the graph for the performance of the YOLOX model, this is the YOLOX large model, and we can compare it with other models such as the YOLO v5 large model, and also the YOLOX darknet 53 model, and efficient det, which is a detector built by Google. And on the x-axis, we have the latency, and here we have the average precision for the COCO dataset. So ideally, we want our model to be on the top left part of the graph because it has low latency and high average precision. And we can see that the YOLOX model outperforms all of the models that were released at the same time because it has higher performance and low latency. And on the right side, we can see that the number of parameters on the x-axis and the average precision on the y-axis. And the YOLOX, the tiny version and the small version of the YOLOX model, there is an increase in performance as we go from the nano version to the small version. And the number of parameters increase because the model is getting larger. But in all the cases, the average precision is higher than the efficient det and the PP YOLO tiny model. And this is just a comparison between the smaller versions of the model for the YOLOX and the efficient det model as compared to the YOLO V for tiny model.